Hello, I'm going to be posting the next couple of lessons on our class YouTube site since several of you are not able to attend in person. I don't want you to get behind. But welcome to the physics semester of physical science. We are no longer talking about chemistry, so if you did not like chemistry, maybe you'll like this better. But if you don't like math, you are probably in for a rude awakening because there's a lot more math in physics than there is in this level of chemistry. So the next few chapters, we are talking about mechanics. So mechanics is the study of motion, not this mechanic who Molly appropriately named Brad. He looks like a Brad. Mechanics is the study of motion. So over the next two chapters, we're talking about how and why objects move. So mechanics is broken into two main branches. We have the first branch, which is kinematics, the study of how things move. How they move from point A to point B, how we describe an object's location, speed, acceleration, velocity, all of that is covered in this chapter on kinematics. The next chapter, chapter 12, we are talking about why things move. So we'll be discussing Newton's laws of motion and forces and whatnot. So how things move and why things move is covered under the umbrella of mechanics, the study of motion. So again, kinematics, the topic of this chapter is the study of how things move. Section 11A, which is what we're covering today, is how can we describe where an object is? How can we describe the location of an object? How can we compare an object's location to the location of another object? So a lot of this is talking about comparison and location, which is defined as an object's position. But first, we need to talk about who Isaac Newton is because his name is going to come up several times in this chapter and next chapter. So Isaac Newton is, or was, a mathematician, physicist, astronomer, theologian, and author. Oofda. Makes me think, what am I doing with my life? I'm only a mom and a wife and a teacher, right? And that seems overwhelming. But I mean, to be fair, he wasn't overwhelmed by technology and distracted by Netflix and TikTok and all these other things. So he had a lot more time on his hands. That's what I'm going to tell myself, to actually change the world. But it's definitely humbling to think of all of these roles that he played in his life and what he contributed to the world, which is a huge deal. He's basically the brainchild of the laws of motion and gravity. So there's more accurate motion. Sorry about that. There are more accurate models of motion that are available today. We know how we talked about models and how their workability is really important. So there's more technically workable models of motion that are available, like the theory of relativity, theories that talk about subatomic particle motion, talk about how electrons orbit around the nucleus, that are super mathematically complex. And they don't really talk about, to the level of our understanding, a simple level, they don't really describe the motion of our everyday objects, the things that we experience in our life. So you and I, we experience physics every day. We wake up, I know that my feet are going to stay on the ground because of the law of gravity. I know that if I kick a soccer ball, it's going to go in the direction of the force that I apply to it because of the laws of motion that Isaac Newton came up with. So we use his laws and his theories to explain the motion of the everyday objects, the everyday experiences that we go through, because they're simple to understand and they still work, right? The math is a lot simpler. And for the purposes of this class, we're not talking about the movement of stars and planets. We're not talking about subatomic particle motion. We're just talking about like the movement of a car or the movement of a ball or the force of gravity. Okay, so that's why we're still going to use Isaac Newton's concepts and ideas because they're simple and they apply to everyday objects. So how do we study motion? All right, I want you to just pause. I want you to freeze and think, are you moving? Okay, well, it depends, right? Technically, yes, you're moving. Every particle, every atom is still technically moving in place because we all have energy, right? But In the sense of your surroundings, if you freeze your body, are you moving? No. So motion is very heavily dependent on perspective. Okay, so everything is relative in the world. So motion is relative to the partaker of the information. So that boils down to what your frame of reference is. So let's break that term down. So a frame, I want you to picture like a picture frame. Okay, a picture frame contains, it has a specific boundary on which you're taking in information. Okay, so my frame of reference right now is my elementary classroom, my computer. I can see the window, but I can't see what's behind me unless I look in my camera, right? So my frame of reference, my perspective or viewpoint, is the information of things that I can see, okay? So my frame, my peripheral vision, and everything in front of me is my frame. The reference is the source of information. So from my perspective, where I'm sitting, my viewpoint is very specific. So if I were to go to the other corner of my classroom, my reference point would be over there, and my frame would be different because I would be facing a different direction. Does that make sense? So motion is very relative to what your perspective is. I want you to think about if you're standing on a street corner and you're watching cars go by. Those cars, to you, in your frame of reference, you looking at the street, those cars are moving. And what are they moving in relation to? They're moving in relation to the stationary objects around them. So the trees in your frame of reference are not moving, but the cars are moving. Any buildings are not moving. They're not sliding down the street, right? Because that would defy the laws of physics. But the cars are moving because a force is applied to the cars. But if you were to take a step back and stand on the moon, which would be epic, everything would be moving, right? The people on the ground would be moving, the trees would be moving, the buildings would be moving, the cars would be moving, because the earth is moving. The earth is rotating on its axis, going around the sun, okay? If you were to, even our galaxy is moving. The Milky Way galaxy is probably rotating within other galaxies, okay? So everything is relative to your perspective, to your reference point, your frame of reference, okay? So where you are, what information are you taking in based on your location? So we can describe an object's position by comparing it to the known location of another object. So if I were to say, my house is located 20 miles northeast of the school. Well, you guys all know where the school is located, right? So that's your point of reference. The object of the known location of the object. So the school's location is known. So if I'm standing at the school, I know I could face the northeast, and if my direction and a distance were accurate, you'd be able to locate my house if I give you that information, which I'm not going to. So in this example, we have a frame of reference, this grid coordinate system. Okay, so this is a frame of reference. And let's say we all know the location of where eye roll is, the eye roll emoji. So the eye roll emoji is right here. We're not going to assign any values to it right now. He's right there. We can see where he's at. And if I were to say that happy, the happy emoji is located 4 squares to the left of eye roll, because you know where eye roll is, you're able to locate where happy is because I gave you a distance and direction to happy's location, to happy's position. What if I were to say happy is 4 squares away from eye roll? Well, that means happy could be anywhere within this 4 square radius, right? So more specifically, I'm giving you a distance and direction to accurately describe happy's position. So now that happy has been located, he can become a point of reference as well. So if I say Wink is 2 squares above happy, if I use my frame of reference, my grid coordinate system, and I say, okay, well, I know that Wink is 2 squares above happy, I can locate Wink. If I were to say Wink is 2 squares away from happy, but I don't give a direction, wink could be anywhere within this radius. Okay, so I want to be specific and give distance and direction from the point of reference, the known location of a given object. So let's do this together. If you're in the boat, so I want you to, maybe you're on a cruise, okay? And all of these objects are on the ground. We're not going to add any third dimensions to this, okay? So there's no z-axis here. There's just the x-axis and the y-axis. So imagine this plane is just sitting on a runway somewhere. So maybe your cruise ship is floating near a runway, an airport. So from your cruise ship, this airplane is what? How would you describe the airplane's location? Well, it depends on your frame of reference. So are you using a coordinate system like this, where you would say, well, it's 1 square to the right and it's 2 squares down? Well, that doesn't really apply to the real world, does it? So say this is in real life. So you could, what's a direction unit that you could use in real life that most people would know? Well, you could use north, south, east, and west, okay? Compass directions. So you could say, well, the plane is southeast of your location, but how far, right? So you would use maybe kilometers or miles to describe an object's location in comparison to you, your known location, because you know where you are. So if I were to say, if somebody were to ask me, hey, where is the nearest plane? Well, I could say, well, the nearest plane is 2 kilometers southeast of our location. And then you would be able to locate where the plane is, okay? But in terms of this frame of reference, this grid coordinate system that we're using, the plane is 1 square to the right and 2 squares down from my location, okay? So that's how we would describe where it's located at. And same thing for the dump truck. The dump truck is 1 square to the left and 3 squares down from my location, from the location of the boat. And same thing for the car. The car is 1 square up and 4 squares to the left of my location. So it really depends on the distance and direction units that you're using and how they apply to the situation that you're in. So what about if an object changes its position? What if it starts somewhere and then it moves and it ends up in a different location? Well, one, I mean, when have you ever thought about this in your life? And 2, what importance does this have to me? So this concept is called displacement, an object's change in position. So in this example, Wink starts here and then he moves 2 squares down, okay? So what if I said Wink moved 2 squares? You'd be like, okay, where? Like he could have moved this way, he could have moved up, he could have moved to the left. So when I talk about a change in position, I need to make sure I include the distance, the amount that the object travels, the magnitude of the travel, as well as the direction in which the object went. Because that's really important. Because if the wink emoji moved to the right, it would have a way different position, a way different final position. So there's actually a mathematical formula that we use to describe an object's displacement or change in position, and that is delta x equals xf minus xi. All right, so let's talk about what each of these things mean. So this triangle is the delta sign, the delta symbol, and whenever you see this triangle before a variable, I want you to mentally apply the words change in. Okay, so if you see a triangle before a variable, it's the delta symbol, and it means change in. So this means change in x. What is x? Well, x is my position. So displacement, delta x, means change in position. Okay, and that is represented by subtracting the initial position from the final position. So once we move on, we're going to have some actual numerical examples to plug into this equation. So just familiarize yourself with this equation, delta x displacement, the change in position is the initial position subtracted from the final position, okay? So wait, all right, so you might be thinking, how are distance and displacement different, okay? So I want you to think about this in terms of what the quantity represents. So distance is literally just how far an object traveled. It doesn't tell you anything more than that. Okay, whereas displacement tells you the distance, but it also gives you more information. It gives you the direction in which the object traveled. So distance is described in displacement, but displacement also gives you more information. It tells you where, okay? It tells you how much and where, all right? So values like these are called scalars and vectors. So distance is an example of a scalar quantity where it's literally just a quantity. It's a magnitude of something. It doesn't tell you anything more than just how much, okay? Whereas a vector, like displacement is a vector quantity. It tells you the quantity of something as well as the direction, okay? So for displacement, it tells you the distance that an object traveled as well as the direction in which the object traveled. Whereas the scalar quantity only tells you the distance, the amount, or the magnitude. So common vector quantities, these are ones that we'll be talking about in this chapter and next, are displacement, distance and direction. We have velocity, which is speed, like miles per hour, speed in a direction. We have acceleration, which is the change in speed in a direction. And then we also have force. So the force of gravity is pulling down, okay? So forces have to go in a direction, all right? Whereas things like temperature, pressure, speed, distance, they don't give you more information about the direction of something. So vectors, vector quantities are represented by arrows because that makes sense, right? To use an arrow symbol to point in a direction of a quantity, okay? So if I say gravity, an arrow pointing down would make logical sense, right? So those arrows depend on, the length of those arrows depend on the magnitude of the quantity that they're representing. So if I have two boats and they're both moving west, maybe one moves west 2 miles and the other one moves west 4 miles, well, the vector arrow that represents the first boat moving 2 miles is going to be shorter than the vector arrow representing the second boat, which is moving 4 miles to the west, okay? So the length of the arrow represents the magnitude of the scalar quantity it represents. So let's do an example. Say you start at point +10 on this number line. So in this example, the number line is our frame of reference, okay? So this is our perspective, all right? We don't see anything else. We don't see any other dimensions. We just see this number line, okay? So in this case, the direction is either going to be positive or negative, okay? We're not going up, down. We're not going to any angles to the side. So our distance is going to be how many units is covered. And then our displacement, our distance and direction is going to be whether it's positive or negative, okay? So you can use direction terms like north, south, east, west, left, right, up, down. You can also use positive and negative to describe displacement as well, to describe the change in position, the change in direction, okay? So we can use all those different terms to describe the direction of position change. So again, in this case, we start at +10 on this number line and say we just moved to B, right? So what is the distance covered? Well, we covered 10, 20, 30 units. Okay, maybe this is miles, maybe this is inches, maybe it's, I don't know, feet. So we covered 30 units of distance. What's our displacement? Well, let's plug it into this formula here. So our final position, because we want to calculate the change in position, displacement, our final position is +40 on this number line, whereas our initial position is +10 on the number line. So we'll plug them into the equation. So the change in x, delta x, equals +40 minus +10, because we just plug those into the equation, and that equals +30. So I didn't add a plus there, but it's kind of implied because there's not a negative. Our displacement, our distance is +30, and our displacement is also +30, okay? So this is an example where distance and displacement are the same thing. where you have a one-dimensional movement. You just move in one direction and you stop, okay? But what happens if you turn around and go back? Okay, how do we measure distance and displacement if we do that? Well, let's add up the total distance traveled. So we have the distance between A and B, which is 30 units. And then we have the distance between B and C, which is 80 units. So my total distance traveled is 110 units, right? So remember that number, 110 units. But our displacement is going to be different because remember, the displacement, the change in position, has to do with the final position and the initial position. So B is kind of just out of the picture at this point because it doesn't count in this displacement equation. So let's plug in the values for the initial position and final position into this formula. So we have delta X displacement equals -40 as our final position minus +10. Okay, so that gives us -50. What does that mean? Okay, so remember we're using plus and minus, positive and negative, to describe direction, in this case for our frame of reference, which is this number line. So negative implies that on the number line, it indicates that it's moving to the left. So I could also say that my displacement is 50 to the left, okay, because that would also be accurate because that also describes the change in the direction for this object, okay, for you. So either saying -50 or saying 50 to the left would be appropriate in this case. So displacement can be positive or negative if the positive and negative describe the direction, okay? So our distance covered was 110 and our displacement was -50. So those are two very, very different values, okay? Distance will always be greater than or equal to displacement. Your displacement will never, ever, ever be greater than your distance, okay? Remember that. So what happens if you can't walk in a straight line somewhere? How do you measure distance and displacement for that? Well, the fastest way from point A to point C would be maybe to take a plane. So it can be advantageous because it takes you the shortest distance by bypassing these obstacles because it adds this other dimension, which is altitude. But we're not going to talk about altitude because that is in more advanced physics. So for the purposes of this class, we're just talking about if we are just moving in 2 dimensions, okay? We're not adding a 3rd dimension of altitude or height. So say this lady needs to get to, maybe this is her house, A is her house, and C is a friend's house to pick something up. But she can't walk this way because maybe there's a lot of traffic, she could get hit by cars, she can't walk through these buildings, so she has to take a different route. So that route is 6 meters to the west, to the east, and then 6 meters to the south to get to her final location, right? That's not actually that far. So these buildings are not to scale. So the 6 meters to the east plus the 6 meters to the south equal 12 meters of distance that she covered. But the displacement, the location of her final position, her final XF is not that far away from A. So think about it this way. If a friend invites you over to her house, maybe she lives a half a mile away as the crow flies. What does that mean? Well, if you were a bird, you could technically like strap on your wings and fly to her house in a straight line, and you would only cover a half mile of distance. But you're not a bird and you have to ride a bike or you have to drive. So you have to get on your bike or get in your car and drive on the roads because you can't drive through people's yards legally. So in order to do that, you cover more distance to go only a half mile because you have to go around all of these objects, okay? So as the crow flies, distance is our displacement in this case. So if you go to a friend's house and you drive 2 miles to get to her house, which is technically only a half mile away, your distance covered is 2 miles, but your displacement, your change in position, is only a half a mile, okay? Because the fastest way from point A to point C in this case is a straight line. So that straight line is our displacement. Well, how did I get this value? Well, that's where the Pythagorean theorem comes in. And I don't want to lose you here, okay? Don't be intimidated by the math, okay? So the Pythagorean theorem is a squared plus b squared equals c squared. And this is applied to right triangles. So let's look at this. If you were like really amazing at walking in a straight line and then turned exactly 90 degrees and walked in a very straight line to get to your location, you would create a perfect right triangle, okay? Because this is 90 degrees right here. Well, we can use the Pythagorean theorem to calculate what this value is. So this is your hypotenuse of the right triangle. So I can say 6 meters squared plus 6 meters squared equals hypotenuse squared, okay? So 6 meters times itself, so 6 squared is 36, plus 36 is 72. So the square root of 72 is 8.49 meters. Okay, so that's how I calculated this distance. I used the Pythagorean theorem. So what happens if maybe this lady went to point C, she picked up what she needed, but now she's going to go back home? So what is the total distance covered? If she goes 6 meters, 6 meters, 6 meters, and 6 meters, well, that's 24 meters total is what she physically walked. Like she did all that work. But what's her displacement? This is kind of a trick question. Because her initial position is A and her final position is A. And if you subtract those from each other, you're going to get 0. So she did all that work and her displacement was 0. She covered 24 meters, but her position didn't change. Okay, it's just like running around a track. Like you could run a full lap around a track, cover 400 meters of distance, but your position didn't change. So your displacement is 0. So it feels like you didn't do any work, but you did. So that's an example of how distance and displacement can be different, can and will be different in most cases. So an example of distance and displacement, this is going to be one of our check on learning questions, of when they're the same, is say if you just start at one point and you walk out to another point and you stop. Okay, so that's an example of when your distance and displacement will be exactly the same. An example of when you would have movement, when your object moves and covers distance but doesn't have any displacement, would be maybe walking around in a circle, like one circle, so, or a lap. So you cover distance, but your displacement is 0. An example of when your distance is going to be greater than displacement is any of these, where you have to walk around an object. Say, I need to walk to the corner of my classroom, but there's desks in the way. So I can't walk in a straight line because I'll run into the desks. So I have to walk around to avoid the obstacles, and I'm going to cover more distance because I have to do that. An example of when displacement is greater than distance is never, because remember, our displacement can never be greater than our distance. Distance is always going to be greater than or equal to displacement. So remember that. So here's a little bit more complex problem before we finish and do our check on learning. So say you are taking a hike in the National Forest. I'm going to turn this video on. Can I? I can't. Okay. So you're taking a hike in the National Forest. You start at this cute little ranger station cabin and you hike in a very straight line. You go exactly 4.5 kilometers east. Okay. And you take a little snack break, eat a Cliff Bar, drink some water. So you may do a little stretching. And then you decide on your second leg, you're going to walk 2.3 meters south, directly south. Like you can make a perfect 90-degree turn. And you walk directly south. There's no trees in your way. This is all very hypothetical, guys. And then you get to your second stop. Maybe you have to have bathroom break, maybe eat another Cliff Bar because you've been doing all that walking, right? Walking over twigs and stuff, burning a lot of energy. So you stop and you turn directions. You make another perfectly 90-degree turn and you walk 5.7 kilometers to the west. So you have now bypassed your starting point. So your starting point, if you were to go directly south, would intersect this line, this vector right here. Okay. So I know that any distance that I cover after this point is going to be 1.2 kilometers. This distance is 5.7 minus this distance, because this is a perfect rectangle because we've got all right angles here. So I know that this is parallel to this. This is parallel to this. So this value, this part of the triangle is going to be 2.3 kilometers. So at this point, I'm exactly 2.3 kilometers south of my starting point. So I know that this side of the right triangle is 2.3 kilometers. This distance is 5.7 kilometers minus 4.5. So I've got this side of the triangle. So now I'm going to plug those numbers into the Pythagorean theorem and solve for my hypotenuse, which is my displacement in this case. So my distance traveled would be 4.5 kilometers plus the 2.3 kilometers that I walked over here, plus the 5.7 kilometers that I walked going west. So 4.5 plus 2.3 plus 5.7 is 12.5, I think. Maybe 12.5. If I'm wrong, I'm sorry. Not a math whiz. So my total distance traveled is all of these vectors added together. But my displacement, so I walked all this distance, but I'm really only this far away from the ranger station. Okay, so let's calculate what this is. So I plug in my 2.3 kilometers over here, 2.3 squared plus 1.2 squared equals c squared. C is my hypotenuse or my displacement. So I simplify 6.73 equals c squared, and then I take the square root of 6.73, and that leaves me with 2.6 kilometers. So I am 2.6 kilometers away from the ranger station. And this is, that gives me the distance away. So that could be anywhere within this radius. If I were to just say I'm 2.6 kilometers away from the ranger station, right? Maybe I need somebody to come rescue me. Well, they're gonna be like, well, what direction are you in from the ranger station? Because we're not gonna send out a search party in all directions. So that's when I need to give them a direction as well. So I am 2.6 kilometers to the southwest of the ranger station. So that could be anywhere in this quadrant, really. Okay. I could get even more specific and I could give them the exact angle. I could give them the exact latitude and longitude of my location. But for the purposes of this class, we are 2.6 kilometers to the southwest of the ranger station. Okay. I hope that makes sense to everybody. All right, so this is our Check on Learning, our exit ticket for this class. So if you have a piece of paper and you have not done so yet, go ahead and get that out and answer these questions. These slides are on Schoology, so if I'm going too fast for you, go ahead and find the slides and write the answers down for these questions. So why is a frame of reference important for describing motion? Why is a frame of reference, a viewpoint or perspective, other words that you could use, important for describing motion? The next question is compare distance and displacement, right? They're similar, but they're different, remember? So distance and displacement, how are they different? Next question is compare scalars and vectors. Okay. Scalar quantities, maybe you can give some examples. Vector quantities, give some examples. How do these things relate to each other? It's very similar to this question on distance and displacement because distance is a scalar quantity and displacement is a vector quantity. All right, next question. What is the distance and displacement for the motion from A to B to C to D as shown in the image below? So if I start here, I move to B, and then C to D, add up your total distance and then come up with the displacement, this value right here. I don't know if you can even see my mouse. Let's pretend you can. Between A and D, what is that displacement? And think about the unit that you're going to use for direction, right? Your frame of reference is this number line. So your direction values are not going to be east or west. It could be to the right, it could be to the left. It could be positive if you're going to the right side of the number line, or if it's negative, you're going to the left side of the number line. So calculate the distance and displacement for this motion. You also need to calculate the distance and displacement for this motion. So if you start at A, this is similar to our hiking path that we took. So we start at A, go to B, go to C, go to D. I want you to calculate the total distance traveled as well as the displacement, or this dotted arrow right here. Okay, and you're going to have to create an imaginary right triangle over here and figure out what the length of these sides are of the triangle to plug into the Pythagorean theorem to calculate this hypotenuse value. Here's a word problem for you. You walk 3 blocks west, so you'll have to draw some vectors here, or arrows. You walk 3 blocks west, then 3 blocks north, and finally 7 blocks south. So what is your distance traveled? So distance in this case is going to be, the unit is going to be blocks, okay? So you walk 3 blocks west, and then add that to 3 blocks north, and add that to 7 blocks south. So that will tell you your total your total distance traveled. Your displacement, again, is going to be similar to this polygon where you draw the vectors and then you connect the last 2 points with a dotted arrow, and then you create an imaginary right triangle to calculate, and then calculate the hypotenuse, your displacement. Okay, all right. In this one, we already talked about, give an example for each kind of motion listed where the distance and displacement are the same. Maybe you can give me a word problem, a real life example of these things. So give me an example of when the distance and displacement are the same, an example of how an object has traveled but has no displacement, an example of when the distance is greater than the displacement, and I better not see any answers for this one because it's a trick question. The displacement is greater than the distance. Okay, because remember, it cannot be. Distance can be equal to or greater than displacement, but displacement can never be greater than distance. Okay, and that is it for today's lecture. Hopefully this was helpful to you. If you have any questions, please email me and I will try to respond as quickly as I can. Have a good day, guys.